Huh. Do you know how to? Do you know how you were able to record? Oh wait, never mind. Nope. Sorry. Anita, you still there? Ah. I'm not seeing an option for me to record. I was thinking I could record and post videos just so students could see the problem solvings that weren't here. But I don't know how to. How do you record?
Maybe you should on your laptop and then give yourself permission to record on your laptop and then record it from there.
Ah, that's a good idea. That's a good idea.
How to do it from an admin perspective.
Yeah. It's weird. You'd think an admin would have a real easy way to record, but let's see. But yeah, for some reason, it just doesn't seem to be. I don't see the option. Let's see. Oops, wrong Zoom. So many Zooms. Group Zoom. Oh no, I don't want to sign in. Shoot. Let's see. Join the meeting. 6, 6, 5, 8, 7, 2, 0. Cool. Yeah, record as a not admin. Oops, that's not gonna work.
Did you mute?
Yeah, there we go. All right, cool. I think I am now. Oh, I got to request permission. I will give me permission. Permission granted. All right, cool. All right, so what questions do you have, Anita?
Is it okay if we go over number 2? I'm getting, I don't know.
2 from chapter 15, I assume, or the exam.
2 from chapter 15.
Okay.
But I'm not even sure if they're right.
Okay. Compute subgame perfect equilibria. Write the normal form matrices, so strategic form for each game, and which ones are not subgame perfect. Good. So this is like this kind of question is like the wheelhouse of what you'll definitely get a question like these two on the final, and so you'll probably get like one of each of these, like one with one with dash lines, one without. The one without dash lines is easier, although the game gets bigger. And then we will there'll probably be one more like Stackelberg. So you can, if there was 3 total SPNE questions, you would expect questions like 2A, 2B, and then Stackelberg, but variations on those things. But that's kind of what to expect. So this is a good question to make sure you understand. So let me go to whiteboard. All right. And now I have to, there we go. Okay, so 2A, so chapter 11, 2A. Here's the game. So we have player 1 who chooses W or Z, who moves to player 2, who's able to see where she's located, and she plays C or D with payoffs of 6, 4, 3, 2. And up here, she can choose A or B, passes on to player 1, who's not able to see which move was made by player 2, who plays X, Y, X, Y, 3, 0, 8, 5, 4, 6, and 2, 1. All right, so the first thing we'll do is we'll put this game into the strategic form, into the matrix. And again, like that's important not only because it's a chapter 15 question, but it's also a chapter 3 question, right? So kind of being able to, so this is kind of, something that we had to do earlier and now we have to do again. So, and yet like time and time again, lots of students end up not being able to put this into the matrix form. So this is a good thing to practice. So what's the size of the strategy space for player 1?
For player 1, it should be 1.
How many strategies does player 1 have available?
So there's W, Z, X, Y, and C, D. So that's going to be 8 because it's 2 times 2 times 2.
No. So close. So how many information sets does player 1 have?
It's actually 4 because it's going to be W, Z, X, and Y.
There you go. So player 1 has 2 information sets. The two nodes that have a dash line between them, that's just one information set. So he doesn't know like I'm in the top one or I'm in the bottom one, so she can't condition information. Like what am I going to do based on where I'm at? She just knows that I'm up there. In player 2 has moved A or B, but I don't know which one it is, so I'm going to choose X or I'm going to choose Y. So player 1's got 2 information sets, and that means every strategy has 2 actions in it. WX, WY, etc. Okay, perfect. And then what about player 2?
For player 2, it's A, B, and it's also C, D. So it's also 4 because it's
Right, perfect. So this is a 4x4. If that dash line for player 1 had not been there, then you would have been right with your first answer. That would have been 8. If the dash line for player 1 was missing, then there would have been X prime and Y prime on the bottom or some other letters. And then there would have been 2 times 2 times 2 elements of the strategy space. But the dash line, so dash lines make the game smaller, and that makes the strategic form smaller. Player 1, player 2, and so we have a WX, WY, ZX, ZY, and then we have A, C, A, D, B, C, B, D, and then we just populate this matrix with payoffs. So if player 1, the easy one is player 1 playing Z. So if player 1 plays Z, and player 2 plays C, we've got the payoff 6-4, and there's going to be a bunch of those. So it doesn't matter what the other actions are because they're not played in this strategy profile. And then the same thing for D. Z and D is 3-2. All right, and then if player 1 chooses W, then we have to look at the actions for player 1 and for player 2. Beyond that, So when player 2 plays A and player 1 plays W, then we're in the top 4, the upper left 4 boxes. And then if player 1 plays X after that, we've got 3, 0, 3, oops. 3, 0, 3, 0. And if player 1 plays Y after that, we have 8, 5, 8, 5. And then W, B from player 2, and then X from player 1 results in 4, 6. And then the last one is 2, 1. Okay? Questions on setting up the matrix? We're good? All right. So next we have to just do our double underline exercise. What are the best responses to find the Nash equilibrium of the full game? So player 1 choosing the first row. The best responses for player 2 are the last 2, B, C, B, D. Over here, they're A, C, A, D. The third row, the best responses are underlined. And here again, best responses are underlined. And now for the column, player 2 plays AC. Player 1's best response is WY. In AD, it's WY. In BC, it's the bottom 2 rows. And in the final column, it's just the top one. And so our Nash equilibria are here, 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 and here. All right. We could write out those Nash equilibria as strategy profiles. So the first profile, we could say Nash equilibrium set is the first one we could say is oops, that's player, tend to go with player 1 first. Doesn't matter. But they could say it's W, X, comma, B, D, W, Y, A, C, W, Y, A, D, Z, X, B, C, and Z, Y, B, C. On an exam, that wouldn't be necessary. If I was just looking for the pure strategy Nash equilibrium profiles, I would circling them would be fine. But just for completeness and to remind us of how to write strategy profile and stuff, that's what I have there. And obviously, there's going to be a whole bunch of mixed strategies in between those, but this game is way too big to worry about mixed strategies for the non-subgame perfect Nash equilibria. Just too many. So this is good for answering the first part, or like it might even be the third part of the question, but like what the game looks like without worrying about subgame perfection. All right. Any questions to this point, Anita? All good? All right. So next we think about the subgames. This game is going to have 3 total subgames. The subgames are this thing up here. Again, the key with subgames, the algorithm for identifying a subgame is pick a node and it initiates a subgame if that node is a singleton, meaning it's not connected to any other nodes with a dashed line. So that's the case here. And it doesn't split up any dash lines. So it doesn't, you have to be able to create a loop around the subgame and never touch a dash line. That's really the kind of the simple process behind. I mean, we talked about in the lectures like the formal definition of what is a subgame, but the implementation when you're looking at a tree is just to pick a node, circle all the successor nodes and branches from that node, and if you never touch the dash line, you're good. If you can't avoid touching a dash line, it's not a subgame. So that's kind of the way to operationalize it. That obviously initiates a subgame, and then the entire game itself is a subgame.
So it's 3, right?
So there's three subgames of this game. I think the book talks about proper subgames, which means like subgames that aren't the whole game. I would never test you on that terminology, but from the book's perspective, this game would have 2 proper subgames and 3 total subgames. And not important vocabulary for me. Okay, so these are 3 games. So I'm going to use maybe I use a different color for to analyze each of the subgame. The red up here. So I'm gonna use red to analyze that subgame below. So we got that's a 2x2. So player 1, player 2. Player 2 starts that subgame, but I'm still going to keep the matrix in the order that we're used to. Rows player 1, columns of player 2, and the payoffs in the same order as they appear in the extensive form. That's not necessary, but I find it to be the easiest way to avoid mistakes. Okay, and player 2 playing A, and so it's 3-0. 2 playing A, and Y is 8-5. XB is 4-6. And BY is 2-1. Okay, and so we can go through our double underline exercise to find the Nash equilibria here. So we have, go ahead.
It'll be XB and AY, right?
Let's see, XB, yes. Yep. So those are our 2 Nash equilibria of the subgame. Okay. And so what this is saying is that a strategy profile that has, a pure strategy profile of the full game that has AX being played in it and that has BY being played, or has BY being played in it, cannot be a Nash equilibrium. It cannot be subgame perfect. Okay, so in other words, only of the pure strategy profiles in the full game, only those profiles that have players playing BX in the top or players playing AY in the top subgame, only those profiles survive subgame perfection. So we can look at the Nash equilibria up above here and see. Let's see, the first one that we have, WXBD. Does that survive?
Yes, because it has
Yes.
XB.
Perfect. What about WYAC?
Yeah, because it has A and Y.
Well, it has, perfect. A and Y, great. And then WYAD for the same reason. What about ZXBC?
It has X and B in it.
Yes. And what about ZY and BC?
This is the one that drops because it doesn't.
Yeah, perfect. Awesome. So that one drops out from game 1. Game 1 kills that one. Or sorry, the sub-game 1. So I'll just put a little red line to it. All right. So so at this point we have that one can't be sub-game perfect because it has in that top sub-game it has player 1 playing Y and player 2 playing B, which is not a part of the Nash equilibrium of the subgame. Okay. So in terms of the Nash equilibria of this subgame, there's actually 3 of them. There's the 2 pure strategies. So we could say that X, so the order is player 1. So we say Nash equilibrium of the subgame, that Nash equilibrium set is XB YA. But we also have a mixed strategy, right? Because we have these 2 pure strategies, so there can be a mixed strategy here. So I am going to put my P's and Q's on this little matrix and solve for the mixed strategy Nash equilibrium. So if player one plays row X, yeah. In order for player one to be willing to mix between X and Y, she has to be indifferent between X and Y. And so the utility of playing X here is 3Q plus 4 times 1 minus Q. And that has to equal her utility of playing Y, which is 8Q plus 2 times 1 minus Q. So that must be true in the mixed strategy equilibrium. So we're going to have here 4 minus Q is equal to 2 minus 6Q, or plus 6Q. So we're going to have, that means 7Q is equal to 2, or Q equals 2/7. Okay, and for the second, for player two, she would need that 0P plus 5 times 1 minus P is equal to 6P plus 1 times 1 minus P. Okay, so she needs that 5 minus 5P equals 1 plus 5P. Oops. Did I 5 minus 6, 1 plus 5P. Oh yeah, sorry. I was worried that I had 2 5Ps and if they had the same sign, then it would have been there couldn't have been a mixed strategy equilibrium here, but they have opposite signs, so I'm fine. Scare myself for a second. 10P equals 4. So P equals 4/10, which is 2/5. So we also have a mixed strategy profile. So sigma 1 equals 2/5, 3/5, and sigma 2 star equals 2/7, 5/7. Okay, and then so we also have the profile sigma 1 star and sigma 2 star as a third Nash equilibrium of the subgame. Okay. All right. So that's the harder subgame. So there's 3 equilibria. There's 2 pure strategies, and there's 1 mixed strategy. And then in the other subgame, I'll do that one in green. That one's super easy. I won't even have to write a matrix. I'll just say if player 2 ends up moving down at that bottom subgame, which one is she going to pick?
Player 2 would pick C.
Correct, because the payoff for player 2 is bigger in C than D. So, in other words, in a subgame perfect Nash equilibrium, player 2 is not allowed to play D. I should have made that a different color, so I'm just going to change that real quick. Okay, and so going back to the Nash equilibria of the full game, which ones does that rule out?
It will blow out WXBD and
Yep.
WYAD.
Yes, perfect. Okay, and so we look at the and so we now look at the full game, and we see that if player 1 chooses W, right? But so we're still not quite done yet, because we have to look at so we have 2 profiles so far that have survived subgame perfection, but they also have to be best responses of the whole game. So if the top subgame is played in the BX equilibrium, that means player 1 is getting 4 and player 2 is getting 6. If instead player 1 chooses Z, what's going to happen? Player 2 is going to choose C, and so player 1 gets 6 and player 1 gets 4. So if, so I'll do this back in black now. If player 1 chooses W, P1 payoff equals payoff, I should say, payoff in BX equilibrium equals 4. And if player 1 chooses Z, player 1 payoff in payoff, it doesn't, in the bottom, there is no equilibrium. Well, we just know player 2 is going to pick C. Playoff, player 1's payoff is, or I should say to keep it, is equals 6, because player 2 will definitely play C. And so player 1, if the top subgame is played in the BX equilibrium, player 1 is definitely going to choose Z. Okay? So player 1 choosing Z, and then and player 2 playing C, and then the top subgame being played in the BX equilibrium is subgame perfect. Okay, does that make sense?
I'm a little confused where you get the Z.
So if you look at the 2 lines above the SPNE, if player 1, so let's suppose, here, let's start this way. Suppose BX equilibrium in top subgame. So let's suppose that these players are going to play the BX equilibrium in the top subgame, because we know they have to play one of the equilibria. So let's suppose they play BX. If they play BX, if in that equilibrium, if knowing that they're going to play the BX equilibrium in the top subgame, if player 1 picks W, then player 1 knows she's going to get 4, right? Because she knows she's going to get 4 in the BX equilibrium. Does that make sense? So by picking W, player 1 knows that red subgame is going to be played in BX, and she knows she's going to get a 4. Do you agree?
Yeah.
So basically, player 1, by choosing W, so like I guess what yeah. So if the top subgame is played in the BX equilibrium, then if player 1 picks W, she's going to get a payoff of 4 for sure. If she picks Z, she's always going to get a payoff of 6, because player 2 picks C, right? We know that for sure. So she get a payoff of 6. So if the top subgame is played in the BX equilibrium, that means that Z is a better choice for player 1 than W. Agree?
Yeah.
So when we wrote down that SPNE, assuming that the top subgame was played in BX, then the only rational choice for player 1 in that at the initial node is Z, and we know for sure that player 2 is going to play C in any subgame perfect Nash equilibrium. So player 1 choosing Z at the bottom node, I'm sorry, at the first node, player 1 choosing Z, and then player 2 choosing C, when they both believe the top subgame will be played BX, that is a subgame perfect Nash equilibrium. So the profile ZX comma BC implements a best response at each node to all the other strategies, and in addition implements an equilibrium in all of the subgames. Does that make sense?
Yeah, I'm just a little confused why we wouldn't choose WYAC.
Well, So that's another possibility, is that the top subgame is played in the YA equilibrium. And that, you're right, that might lead player one to make a different choice, right? Player one, if the top, so you got to remember, in an equilibrium, everybody knows what everyone does, and everyone makes a best response in accordance with what everyone else does. So when I ask, can BX, the equilibrium of the top subgame, can that be part of a subgame perfect Nash equilibrium? Then I'm saying, okay, if that BX is played in the top subgame, then player one's response to playing the BX equilibrium in the top subgame must be rational and respect common knowledge of rationality. So if they know that BX is going to be the equilibrium of the top subgame, and they know that C is going to be played in the bottom subgame, then player one knows that she should play bottom at the initial node, because she's allowed to know for sure what the equilibria are in each of the other subgames. It's a little bit weird that she's like, well, I mean, wouldn't she rather that AY be played in the top subgame? Well, yeah, because she gets a payoff of 8 up there, but she doesn't get to impose which equilibrium they're going to be paid in the top game. We have to consider the possibility that either one of the equilibria are played, and then once we propose it, it becomes fact. Now, there are things you can think about as to of the subgame perfect Nash equilibrium. Since player one gets to move first, shouldn't she take a move in the direction of the equilibrium that gives a bigger payoff? There are reasons to think that's true, but we're not going to talk about that in this class. That kind of selecting from amongst subgame perfect Nash equilibrium goes beyond what we're going to learn in the class. So it's true that what we've just written is a subgame perfect Nash equilibrium. It's going to be true that there's another subgame perfect Nash equilibrium that has player one choosing W, and player one's going to like that equilibrium more. But just like the coordination game, the Pareto coordination game, where both players' interests are aligned. Like in one corner they have like 2-2, in the opposite corner they have 1-1 payoffs, and in the other two corners they have 0-0. Both of the 2-2 and the 1-1 are both Nash equilibria. Both players prefer one of the equilibria to the other, but that doesn't mean that the other one that has the inferior equilibrium is never played. Like it is an equilibrium. If both players believe that both players are going to play the bottom equilibrium, it becomes a self-fulfilling prophecy. And we would expect the equilibrium with the higher payoffs to be played more frequently, or to be more likely to be played, but the other one's still in equilibrium. So here we're going to have two pure strategy subgame perfect Nash equilibria. It could be the case that player one, recognizing that both are subgame perfect, wants to encourage the one with higher payoffs for player one, so she picks choice W, hoping to push player two into the other subgame perfect Nash equilibrium. But we're not going to talk about those kind of selection strategies from amongst SPNE. All we're trying to do right now is to identify all of the SPNE, and that would be a more advanced topic, is how can players select from amongst the SPNE. Does that all make sense?
Yeah, that makes sense.
Okay, so what we've done here is both players are assuming that the top subgame is played in BX and the bottom subgame is played as C, and then we just want to figure out what does player one do in response to those other subgame to the equilibria of the subgames. Player one's response is to play Z, and so that makes it an SPNE. But you're absolutely right. The other equilibrium, suppose AY.
We have to consider BX because like player 2 wants 6 because 6 is bigger than 5, right?
Well, it all comes down to player one, because we already know. So let's assume YA is the equilibrium of the top subgame. So we already, so basically player one, by choosing W, knows that her payoff is 8. Right?
Yeah.
And she knows if she plays Z, her payoff is 6.
Mm-hmm.
Which means that player one, so P1 knows just erase my box. Player one knows her payoff equals 8. And if P1 chooses Z, payoff equals 6. So choose W, right? So if she knows by picking W, her payoff is 8. And if she picks Z, her payoff is 6. Of course, she picks W. So the profile W for player one, and then playing Y in the top subgame, and then player two plays A in the top subgame, and plays C in the bottom subgame. That is SPNE. And I have is SPN. Okay? So WYAC is subgame perfect, and ZXBC is also subgame perfect. Both of those strategy profiles implement a subgame perfect, implement a Nash equilibrium of every subgame, including the whole game. All right? So basically, the idea is that if the top subgame is played in AY, it forces player one to pick W over Z because her payoff is bigger by picking W. But if the top subgame is played in BX, player one's payoff at Z is bigger than her payoff in W, so forcing player one to pick Z at the initial node. So both of those are Nash equilibria. And I think your mind naturally went to the place, well, player one's payoff is bigger in the WYAC equilibrium. So why doesn't player one pick W all the time? And the answer is, well, if player one believes player two's strategy is BC, then player one's best response is to pick ZX. So because if she picked W and player two does play BC, then player one is going to get lower payoffs. WBC winds, WY, W, and then player two picks B, player one is looking at a payoff of 4 or 2, which is worse than if she had just played Z, right? So again, like there's two subgame perfect Nash equilibria, it makes sense to think that player one looks at those two equilibria and says, well, I like the WYAC equilibrium more, so I'm just going to pick W and force that equilibrium. But that would not be the right response to player one believing that player two plays BC. So an equilibrium is defined as I make a guess about the other player, I give a best response to that guess, and everyone's guesses are correct. So if I'm player one and I really think that player two is going to play BC, I should play ZX, right? And if player two thinks I'm going to play ZX, then player two should play BC. And so that is a Nash equilibria, and it implements an equilibrium in every subgame. But I agree that if we're going to take equilibrium seriously, and so, which then says, well, then they can't play out of equilibrium. So if player one chooses W, that means that if she knows that everything else is going to be played in equilibrium, she must be able to force the top equilibrium. So I mean, it's a really important and interesting idea, but it's one that goes beyond the scope of the class. They're both equilibria. They're both subgame perfect. Which one is a more reasonable one to think people are going to play? That becomes a debate that goes beyond this class. All right, does that all make sense?
Yeah.
Okay, but we're not done. So there's still one more subgame perfect Nash equilibrium, but this one involves mixed strategies. But it's still useful to think about. All right, so we have to think about what is the mixed strategy payoff of player one if the top subgame is played in the mixed strategy equilibrium. That mixed strategy equilibrium results in an expected payoff of player one. If that expected payoff for player one is bigger than 6, which is, she already knows what her payoff of picking Z is. If the expected payoff of the mixed strategy is bigger than 6, then she's going to play the W. And if the expected payoff of the mixed strategy equilibrium is less than 6, then she'll play Z. So we also have to think about that mixed strategy equilibrium. So the first thing we have to do there is to identify what are the payoffs of the mixed strategy equilibrium of the top subgame. Okay, so and in particular, we only have to work out the payoffs for player one. So we have to work out the payoffs for player one of playing that equilibrium. Okay, I'm going to squeeze just so we're still on the same page. I'm going to squeeze those equilibria into here. Mixed strategy Nash equilibrium pay for player one. Okay, so squeeze those into here. So if player two is choosing Q equals 2/7, then player one's payoff of playing X is 3 times 2/7 plus 4 times 5/7. Okay, and we know her payoff of playing Y is the same thing. So we know that 8 times 2/7 plus 5 times 5/7, or 2 times 5/7 is going to give the same expected payoff. Now I look at this and I can already see for sure that that payoff is going to be a number between 3 and 4. And so whatever that payoff is, player one is going to play Z instead of W. Because if she plays W and the top subgame is played in the mixed strategy Nash equilibrium, her payoff is going to be somewhere between 3 and 4, and she's better off playing Z. But just for completeness, let's just write down what that payoff is. That's going to be 6/7 plus 20/7. So 4 times, 20. So 26/7. All right, which equals 26/7, which equals 3 5/7. Okay, which is smaller. So actually, I should write. So playing W gives payoff to player one of 3 5/7, and Z gives 6, so play Z. Okay, so in that mixed strategy equilibrium, she's going to play Z, and so I'll write, let's do that whole thing in orange. So given that information, I'm going to squeeze that equilibrium down here. So player one strategy profile, if we look up at the matrix of the whole game, we can see this is position. So going down the rows, WX is the first one, WY is the second, ZX and ZY are the third and fourth. Okay, so how much weight. So given what we just did in that that circled area up there, what is the probability that player one chooses strategy WX in this equilibrium?
They wouldn't choose it.
Correct. Perfect. So sigma 1 here equals 0 in the first position. What's the probability she plays WY?
Two-seventh.
No, not WY, because it starts with a W, and we know she's not going to play W, right?
So two-thirds.
No. So we know that if the top subgame is played in the mixed strategy, 2/7, for 2/7 for player 2, 2/5 for player 1 on the top strategies, we know that player 1's payoff is 3 and 5/7. We know if she picked Z, her payoff is 6. So player 1 in any mixed strategy, in any subgame perfect Nash equilibrium that plays the mixed strategy in the top subgame, player 1 will definitely play Z. So anything with a W in it is out. She puts no probability on those strategies because she definitely doesn't play W. So the first two are zeros, all right? But now, what's the probability that she plays both Z and X? Well, we know she plays Z for sure. What's the probability she plays X?
Two-sevenths.
No, that's the probability that player 2 plays A. The probability that player 1 plays X is 2/5, right? Because P is the probability for player 1, right? So player 1 is going to play ZX 2/5 of the time, and then she'll play ZY 3/5 of the time. So that means that since those two add up to 1, she plays Z every single time. But in the top sub game, she plays X 2/5 of the time, and the bottom, and then she plays Y 3/5 of the time. Okay.
Okay.
And for player 2, what we know is that she never plays D, right? So anything with a D in it is out. That's the second and the fourth strategies in the matrix above, right? So A, D, and BD are out. AC and BC are going to add up to 1. What's the probability she plays A? Well, that's Q, right? And that's 2. What's that?
It will be 2/7,
Yes.
0, 5/7, 0.
Perfect. Oops. I missed up the order. Sorry about that. She plays C for sure. Oops. So AC is 2/7, and then 0, and then 5/7, and then 0 is SP and E. Okay. So we've identified 3 total subgame perfect Nash equilibria, the 2 that we circled of the pure strategy equilibrias, and then this 1 additional mixed strategy equilibria. So there's exactly 3 subgame perfect Nash equilibrium of this game. 2 of them are pure strategies. 1 of them is a mixed strategy. There are 5 Nash equilibria that are pure strategies of the full game. There are countless mixed strategy equilibria of the full game. We're never going to try to identify those. There's way too many. Okay? But the key to finishing it off, everything seemed very clear for you when we found the equilibria of the top subgame. We found the real simple equilibrium of the bottom subgame. Then the final key is to anticipate what player 1 does at the initial node, given the equilibrium that's going to be played in the other subgames. And so for that,
we have to assume, hey, in this subgame, this equilibrium's played. What does that do to player one by backward induction, right? So we basically, if the BX equilibrium is played in the top subgame, all player one needs to know is, oh, if I play W, my payoff is 4, right? She doesn't need to know anything about the game. She just knows, hey, if that's the equilibrium, then I reduce that entire subgame. I reduce it to a payoff of 4. That's all I care about, right? So she simplifies it dramatically. She's like, oh, that's a 4. That's a, basically I'm looking at a game where if I play W, I get 4. If I play Z, I get 6. So I pick Z, right? She just reduces the subgame to a payoff or an expected payoff if it's a mixed strategy. All right. And then we identify all of those combinations. So yeah, this game is tricky in, each subgame, the equilibrium is simple, but then we have to think about how that interacts with the full game and player's initial choice. She has to assume if this equilibrium is played in the top and this equilibrium is played in the bottom, what do I do? And then that's going to be subgame perfect. Okay?
Okay.
Awesome. And then let's see. Oh, you're still the only one here. I hadn't looked at and then you're at 2B. I'm guessing this one's going to be simpler. Let's see. So number 15, 2B. Well, it's chapter 15. We have the following game. UD A B results in 2, 3, 5, 4, and then down here. So we say a game like this, because there's no dash lines, every single person at every single node knows exactly what has happened in the game to that point. We call these games of perfect information. So games of perfect information are pretty easy to solve by backward induction. They're simpler games, but they tend to be larger in the extensive, the normal form of the game. What's the size of this one? How many for player one and how many player two? The strategy space for each?
So it'll be 4 for player 1.
Mm-hmm.
And then for player 2, also be 4.
Yes. So this one's going to be a 4x4. So each player has 2 information sets, 2 actions in each information set. So player 1, A, C, A, D, B, C, B, D. And player 2 has, oh shoot, that I just did player 2's payoffs. A C A D B C B D. Now I have to erase those and replace them for player 1. Okay. U E U F D E D F. And then the payoffs of playing U and player 2 playing A are 2, 3. Player 2 plays B, they're 5, 4. And then if player 1 chooses down, and if player 2 chooses down, this is also an easy one. We have 0, 2. This looks to me like it's suspiciously a non-credible threat. Player 2 is going to threaten to go to D, which is going to make player 1 give player 2 payoff by picking F, but that's not going to survive subgame perfect Nash equilibria. You see what I mean? Mm-hmm. I'm looking at that game and I'm like, if player 2 says, I'm going to play D if you go down, then I'm going to give you a payoff of 0 and me a payoff of 2. And then player 1 says, oh, wow, if you do that, then I better you're trying to avoid me picking the E up here and getting a 6 and a 2. So you're trying to get me to go up at the first decision node, right? Instead of picking the F in the bottom one. So anyway, but
with that. DEAC results in a payoff of 6-2. So D, if I see a D, a C, and an E, we're always going to get 6-2. And otherwise we get 2-6. All right, and the equilibria, the pure strategy equilibria, across the row, we get those payoffs as best response. These are all best responses in that row. Looks like a possible many equilibria here. In this column, only one best response. Here we have, so the responses of player 2, there's not as many best responses. And so the set of pure strategy Nash equilibria are this one, this one, this one, and this one. Okay, 4 of them. I'm not going to bother writing them out, but those are the 4 pure strategy Nash equilibria. Okay, subgame perfection. Let's see if we can get away with this by just circling stuff. So first of all, there are how many total subgames?
4.
Perfect. 4 subgames. Each of those subgames must be played in equilibrium, but we solve the equilibria by backward induction. So each of the subgames actually becomes reduced to just a player picking the one that gives them the biggest payoff, right? So if we're in so if player 1 picks up and player 2 choosing between A and B, which one of those does player 2 pick, A or B?
B.
Right. So any equilibrium that is subgame perfect must have player 2 picking B in that information set. Okay. If player 1 chooses down, and if player 2 picks C, what does player 1 do? Does she pick E or does she pick F?
E.
Right. She picks E because the payoff is bigger. Okay. So that subgame reduces to a payoff of 6-2. And if that game reduces to a payoff of 6-2, what does player 2 do? Does she pick C or does she pick D?
Player 2.
Yes.
They're the same payoff.
Yeah, this is the only tricky spot of this game. They're both best responses. So so we know for sure that player 1 is going to pick E, which means that we know player 2 could play C or D, which then makes player 1's choice of U and D a little bit trickier, because if she believes, if in the equilibrium, if player 2 is picking C, then she knows she gets a payoff of 6, and that's really good. But if she thinks player 2 is picking a payoff of D, then that's really bad for player 1. Okay? So so now we look from the perspective of player 1 at the initial node. Does she play U or D? That's going to depend on which of those 2 equilibria she thinks player 2 is going to do, right? So let's imagine, suppose, here, let's do it this way. Let's look at this subgame. This subgame has 2 equilibria, right? Player 1 is always going to pick E, but player 2 could pick C, or player 1 could pick E and player 2 could get D, are both S, P, and E of subgame. All right? So they both have player 1 choosing E in the littlest subgame, and they both implement an equilibrium of the overall subgame, right? So EC and ED are both possible. EC, the payoff to player 1 equals what? So if that bottom subgame, and circled in red, with the 2 together, if that bottom subgame is played in the EC equilibrium, what's the payoff of player 1?
The payoff would be 6.
Correct.
And what about this other one, ED? What's the payoff of player 1?
It would be 0.
Yes. Okay. Now, both of those are possibility in subgame perfect Nash equilibrium. So what if player 1 believes and player 2 believes that the red subgame is played in equilibrium EC? What should player 1 do? Pick U or pick D?
They would pick D because they would get 6 instead of 5.
That's perfect. So D for player 1. And then in that subgame, player 1 is also playing E. And we know that player 2 has to play B up top, always. And in this equilibrium, player 2 is playing C in the bottom. That is subgame perfect. Everyone is best responding to their beliefs about everyone else, and every subgame is played in equilibrium. Okay? And now we look at the other equilibrium. Okay? So we look at the ED equilibrium. And now we think about player 1 at the first decision node. What is player 1 going to do? Pick U or pick D?
For the other one, player
Uh-huh.
choose U for sure.
Yeah, for sure. So player 1 picks U. And then we know that in that equilibrium, player 1 is also playing E. We also know that player 2 has to play B at the top. And finally, what's player 2 doing in the bottom? Well, in this equilibrium, she's picking D. Okay? So if player 1 and player 2 believe the bottom subgame are going to be played in the ED equilibrium, then player 1 is going to choose U. And otherwise, if they play in the EC equilibrium, player 1 is going to pick D. And so those two are pure strategy subgame perfect Nash equilibrium. So we could, going back to the original game, we see that one of them is here, and then UEBD is this one. So of the original ones, of the pure strategies, 2 of them are subgame perfect, and 2 of them are not. Okay. And then finally, we also have to think about player 2 mixing between C and D because she's indifferent between them, right? So player 2 could also mix between C and D. And now whether player 1 picks U or D is going to depend on what the fraction that player 2 puts on C is, right? So if sigma 2 equals Q and 1 minus Q, right? Player 1's payoff of player 2 mixing like Q and 1 minus Q, player 1's payoff is going to be, well, if player 1 plays C with probability Q, player 1's payoff is 6 times Q, and then it's plus 0 times 1 minus Q equals 6Q, right? And so player 1 plays D if 6Q is greater than 5, the payoff of picking U. So if Q is greater than 5, 6. So let's see. So player 1 picking D, and then E, and then player 2 playing sigma 2 is SPNE
if, and these should be greater than or equal to, if Q greater than or equal to 5, 6, and otherwise player 1 playing U and then E, and player 2 playing sigma 2 is S, P, N, E if Q is less than or equal to 5, 6. And so now you notice that if Q is equal to exactly 5, 6, then player 1 is indifferent between U and D. So player 1 would be willing to do any mixture in between them. But if player 1 is mixing between U and D, that's giving a payoff to player 2 of something between 3 and 4. But then player 1 is not going to mix. Oh, no, she can mix between C and D, right? But that, so, no, because she has to play B up there. So think this through. So if player 2 plays the bottom exactly 5, 6, player 1 is indifferent between top and bottom, between U and D. And if player 1 is indifferent between U and D, player 2 plays B at the top for sure, getting payoff 4. And she picks, she's still indifferent between C and D in the event that player 1 plays at the bottom. Yeah. So there's also an equilibrium where player 1, any mix of D, E, D, U, if if sigma 2 equals 5 over 6 comma 1 over 6. All right. So player 1, her payoffs are equal no matter whether she plays any mix of, that would be U, E, and DE. So that would be like sigma 1 equal. So she never puts any weight on playing F. So sigma 1, I'm out of room down there. Sigma 1 equals, she never plays the second or the fourth strategies because they have F's in them. So P, comma, 0, comma, 1 minus P, comma, 0, any P in the 0, 1 interval. I keep hitting the camera icon when I try to write in down there. Yeah, it's not, I'm not able to write it there, so.
Maybe in the top right-hand corner.
I'll just put it right here, any P in 0, 1.
That says any at the bottom, right?
Yes. Okay. So there's 1, 2, and this one, 3. So in that case, since I already talked about the equals case, so it's like player 1 could play pure strategy D or pure strategy U if Q is exactly equal to 5, 6, but he could also play any mixture of the two. So technically, we wouldn't need the greater than or equal to and less than or equal to. We could just do greater and less than. So player 1 has to play D if Q is greater than 5 fifths. Player 1 has to play U if Q is less than 5, 6. And if Q is exactly equal to 5, 6, player 1 can do anything she wants. Okay.
Okay.
All right. Yeah. So those games were more work than I thought, but very useful work. I would say, in both of the games, are interesting or are tricky. In this game is tricky because of the indifference of player two. So that makes it tougher. Like these games that have of perfect information, they're typically very, very easy to solve if there's no ties for a player. As soon as a player has ties, like if player two is indifferent, his indifference is for player two, it doesn't matter what she does, but for player one, it can matter a lot. And so games of perfect information, if there's no ties, are super easy to solve. There's a unique subgame perfect Nash equilibrium. As soon as there's ties, it can open up a lot of different possibilities. So that second game was made tricky by the fact that there's a tie for player two, but that's why he put that game in there. And in the first game is made tricky because in the top subgame, there was two pure strategy equilibria plus a mixture in between, which makes the analysis of that game, you have to look at a lot of different cases. So again, if that top subgame had a unique pure strategy equilibrium, that also would have been a much, much easier game to solve. So it's, but the good news is that when I give you a game to solve on the exam, they're not going to be any bigger than what you see here, and they're not going to be any trickier than what you see here. So if you can solve both of these games, you're perfectly well prepared to solve any question of this form that I give you on the exam. So if I give you an extensive form game, ask you to find the pure strategy Nash equilibria, ask you to identify any subgame perfect Nash equilibria. If you can do question 2, you can do any question on my exam. These are as hard as they get. And these are as hard as any question I'm going to give to you. They won't be any harder than this. And probably one will be like this level of hard and one will be easier.
Okay.
Okay. So if you can kind of get comfortable with this game, these two games, you're perfectly ready.
Okay, so I'm gonna do this a few more times because I feel like I was missing part of the SPNEs.
Okay.
I would just ignore the other ones because I didn't
Okay.
realize there was like so many.
Yeah.
And
Yeah, it's because of the multiplicity, right? Again, for player two, because player two can do two different things in part B, it opens up various things for player one. And because there's two in the first and part A, because there's two pure strategy equilibria and a mixed strategy equilibrium of the top subgame, it creates a lot of possibilities overall. So SPNEs, if every subgame is reduced to a single possibility, then the subgame perfect Nash equilibrium is going to be unique, right? If everything resolves to a single possibility, every subgame, then every equilibrium is unique. But here, the problem is that we had multiplicity. And multiplicity means there's going to be multiple SPNEs.
which Nash equilibria are not subgame perfect? Would it be the UFBD one?
In part B?
Yeah, for part B.
Yes, UFBD is not, and DEAC is not. And then there's also going to be mixed strategy equilibria of the whole game, but we're not going to worry about those. If you have a 4x4 game, I will never, ever, ever make you find the mixed strategy Nash equilibria. Just too many of them. So don't worry. So for the full game, never worry about the mixes. Just worry about the pures. For the SPNEs, you'll have to worry about the mixes, but I'll make sure that there's not a crazy amount of them.
Okay, and for the exam,
Yes.
will there be a curve?
That depends on how students do on the exam. So I won't give less than 50% A's and B's for the class for sure. There'll be more than 50% A's and B's. Usually I set it to around 55 or so. And so I've gone as high as almost as high as like 60, as 2/3 of the class in a class that was just doing really, really well. So what I'll do is take your midterm grade plus the final grade and average the score, not the midterm grade, the first half of the semester grade. Like yours is 100% right now. So you take that 100 take the final, average the two together. That's your course percentage. And then if the median student in the class has less than 80% on that average, I'll raise everyone enough points to make sure the median student gets at least a B minus. So that depends on how the rest of the class does. The median grade in the class right now is around, I think it's a 90, and I think the average is like 88 or something like that. Maybe they're reversed, but I think the median is 90 and the average is 88. So if the median student on the course to this point gets less than a 70% on the final, then the median average would be less than 90%. I'm sorry, less than 80%, and so I'll have to curve. So basically, if the typical student on the final does worse than a 70%, I'll probably end up curving some. And if the typical student on the final does better than 70%, I probably won't end up curving.
Okay, so you
All right.
made a game plan for yourself.
Oh, I didn't even make it. It's the plan I've had. I mean, it's the way I've graded since I started at Baruch. So there's really no. So basically, if I never curve negatively, so if 80% of the students finished above an 80%, I'd be super happy to give out 80% A's and B's. Like it's not. I would never curve down, or up, whatever that is. I would never you got it. You got an 80%, but I'm going to give you a C because too many people got B's. I'd never do that. But if not enough students get A's and B's, I always make sure that at least half the class gets A's and B's, because that seems to be fairly typical of the distribution of grades in economics courses. They're kind of looking for something around that number. So I'm not averse to going above it, but I don't want to go below it. So, and it's a hard class, so I usually do end up curving. But for you guys, because of coronavirus, the way that we did the midterm plus the quizzes, and because I knew that was going to be chaotic, I kind of was real generous with the curving for that, kind of dropping 30 full points. So I've already done a lot of curving, which means a lot of students are already kind of near the max of what they could be. And so I might not have to do much curving of the final.
Okay.
Cool.
Well, questions like this take a kind of a big chunk of time. How many questions do you think you're gonna put on the final?
Well, so that it's hard to say, because a question like this, I would subdivide into a bunch of parts. So you would get points for taking that extensive form game and putting it into the matrix form. So that's a certain number of points right there. You would get points for then identifying the Nash equilibria, right? Because that's chapter 9, right? And then, so that's some points. And then you're trying to find the subgame perfect Nash equilibrium. So that's chapter 15. So a question like this could be structured into a couple of questions. Like question 1, transform this extensive form game into the strategic form. Question 2, now find this SPNE. So given, I will make it so that the target amount of finish, you should be able to finish it if you're well prepared in 2 hours, and you're going to have 2.5 hours, which means that you have some time for tech glitches and all that other stuff. So I don't think it's going to be more significantly more questions than the midterm in terms of, but the thing is, this exam will have some questions that are very easy to answer because they're from earlier chapters. So I can ask more questions but still have it take the same amount of time as the midterm. So yeah. So ideally, I think the midterm had 12 questions. Is that right?
I think,
or 15.
I think it was 14 or 15.
15 questions, 4 points each, would have made it 60 points. I think that's what I did, 15 questions. So you can expect that there be 20 questions on the final, but some of those questions should be really easy to answer because there wasn't a whole lot of really easy ones on the midterm because it was from the middle chapters, and some of those chapters are pretty hard. So it's like, you could get a game and just have to identify the pure strategy Nash equilibria, and that could be a question because that's like a chapter 9 question, and an easy chapter 9 question. Or I could give you a particular belief, and then, hey, what's player one's best response set? That's a question. So there'll be some questions that'll be kind of easier. So yeah, let's say 20 questions, 5 points each. But some of the questions will be pretty easy. So they won't take much calculation.
Okay.
All right.
Thank you.
All right. See you next week. Oh no, wait, what's today? Oh, Wednesday. Yeah. See you next week.
Thank you so much.
All right. Bye-bye.
Bye.